Welcome to qnawire.
Let's draw a force diagram for the pilot at the top of the loop. So at top, the force diagram looks like this. This is the pilot. This is the only force on him at this point, mg. And we have a radial acceleration downward because he's swinging in the circle right here and he's at the top. And so the sum of the forces in the y is equal to the mass times acceleration of the y. This implies that mass times g is equal to mass times a rad, which implies that g is equal to v squared over r. I canceled m and wrote down the expression for the radial acceleration, which is equal to v squared over r. And then now I can solve this for v at the top of the loop. This gives v is equal to the square root of g times r. And then plugging in values for g and r, which are given in the problem, I get 38.34 meters per second. Now, we move on to part B, and the key idea for part B is that the apparent weight is the normal force that the chair is exerting on the pilot. And so if we solve for the normal force, we get the apparent weight, which is what part B is asking for. So first I'm going to draw a force diagram for the bottom now. So the bottom of the loop. We have gravity still pulling us down. We have an acceleration upward, and it's a radial acceleration still. And we have a normal force keeping the pilot from flying out of the plane. So it's directed upwards when he's at the bottom of the loop. And so we do Newton's second law in the y direction. Sum of the force in the y is equal to mass times acceleration in the y. This implies that the normal force minus mg is equal to mv squared over r. And now, before we can solve this for the normal force, we need to know what the mass is. We're told in the problem that the weight is 700 newtons, the true weight of the pilot. And so mass is equal to weight over g. And so when we divide this by 9.8, we get a mass of 71.43 kilograms. We're also given the velocity, but we're given it in different units than we need. We're given it in 280 kilometers per hour. So let's convert this to meters per second. So I'm going to convert hours to seconds first. 1 hour is 3,600 seconds. Cancel the hours. And then now I'm going to convert the kilometers into meters. So kilometers in the bottom, meters in the top. 1 kilometer is 1,000 meters. And so when I do 280 times 1,000 divided by 3,600, I get 77.8 meters per second. Now these are the values I plug in here. I plug in 71.43 for mass, 77.8 for v, and then r is given and was used in part A, and I solve for n here. When I do that, I get n is equal to 3,580 newtons. This is the force the chair exerts on the pilot to keep him from falling out of the plane and keep him in the loop. And this is the apparent weight of the pilot. And so this is the final answer to part B.